Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today we're diving into a really fascinating, and frankly a bit unsettling, study out of Harvard and MIT. It claims that large language models, LLMs, fail to demonstrate an internal world model. What do you all think? Big news or overblown?
I think it's both, actually. It's not surprising because we've seen these limitations for a while. But it is big news because it throws into sharp relief the fundamental problems we're facing with just scaling up current deep learning architectures. I mean, we've been hoping that more data would magically create these internal models. And it seems it's not happening, right?
Exactly. I've been saying this for ages. Throwing more data at the problem is like trying to build a house by just piling up bricks without a blueprint. You might get something that looks like a house from the outside, but it's not going to be structurally sound, and it's definitely not going to function like a house. And this lack of an internal model, it's a design flaw, not just a matter of lacking data.
I agree. And I think the problem is even more fundamental than just a lack of a blueprint. I think it's a lack of understanding of the foundational principles of building. It's like if we're building an LLM to understand spatial relationships, current deep learning is trying to do that without understanding coordinate transformations. They can sort of approximate it, but they don't actually understand how different coordinate systems relate to each other. So yeah, brute force.
So let's unpack that a bit. For our listeners who might not be as familiar, what is an internal world model and why is it so important?
Okay, simply put, an internal world model is a representation of the environment, its objects, and their relationships that an agent, whether it's a human, an animal, or an AI, uses to reason, plan, and act in the world. It's how you predict what will happen if you push a cup off the table, or how you navigate a crowded room without bumping into people. It's not just about recognizing patterns, it's about understanding the underlying dynamics and causal relationships.
Yes, and it's not just a static picture either. It's a dynamic, constantly updating representation. Think about driving a car. You're not just seeing the road, you're constantly predicting where other cars are going to be, anticipating potential hazards, and adjusting your course accordingly. That's all based on your internal world model of traffic and physics.
Exactly. And that model isn't just visual. It integrates information from all your senses, your sense of balance, the sound of the engine, the feel of the steering wheel. And it represents that information in a way that allows you to reason about it. Like, if you hear a siren behind you, you know what that means in the context of traffic laws and your own driving behavior.
Okay, so LLMs, according to the study, are lacking this. What did they do in the study to determine this? What experiments did they run?
Well, the study used a variety of clever techniques to probe the internal representations of these models. One key thing they looked at was the consistency of the model's responses across different phrasings of the same question. If a model truly understands the underlying concept, it should be able to answer the question correctly regardless of how it's worded. But they found that LLMs were often tripped up by subtle changes in wording, suggesting they were relying on surface-level patterns rather than a deeper understanding.
Right, it's like asking a child who's memorized their multiplication tables what 7 times 8 is they can rattle off 56 no problem. But if you ask them how many groups of 8 you can make from 56 objects, they might struggle because they haven't actually grasped the concept of multiplication, just the rote memorization.
And another key aspect was their ability to handle counterfactuals. Like, if you ask an LLM, what would have happened if the red ball had hit the blue ball? A true internal model should allow it to simulate that scenario and predict the outcome based on physical principles. But the study found that LLMs often struggled with these kinds of questions, again suggesting a lack of true understanding of the underlying dynamics.
So they're not able to mentally simulate a different reality and reason about it.
Exactly. They're good at predicting the most likely outcome based on past data, but they're not good at reasoning about possible outcomes based on underlying principles.
Okay, so given this lack of an internal world model, what are the practical implications? What are the limitations of current LLMs in real-world applications?
Well, the most obvious limitation is their inability to handle situations they haven't seen before. Because they're relying on pattern matching, they're easily thrown off by novel inputs or unexpected events. Think about self-driving cars. They can handle most everyday driving situations pretty well, but they still struggle with unexpected events like construction zones, unusual weather conditions, or aggressive drivers. That's because their internal world model isn't robust enough to handle these novel situations.
And it's not just self-driving cars. Think about medical diagnosis. An LLM might be able to identify patterns in medical images that are indicative of a particular disease, but it might not be able to reason about the underlying physiological mechanisms or understand the potential side effects of different treatments. So, it can be a useful tool for doctors, but it can't replace their clinical judgment.
Or think about robotics. An LLM might be able to control a robot to perform a specific task in a controlled environment, but it might not be able to adapt to changes in the environment or recover from unexpected errors. Like, if you ask a robot to make a sandwich, it might be able to follow a set of instructions perfectly, but if the bread is stale or the knife is dull, it won't be able to figure out how to solve the problem because it doesn't understand the underlying physics of cutting and spreading.
Right, so they are very brittle. They're not adaptable. They're not truly understanding the world they're operating in. This resonates with something else I've been reading about recently, this idea of emergent misalignment and narrow fine-tuning of LLMs. Essentially, when you train these models to be really good at one specific task, it can sometimes lead to unexpected and undesirable behaviors in other areas. It's like they become too specialized and they lose their overall understanding of the world, becoming misaligned with broader goals.
That's a scary thought, actually. It's like we're trying to build these super intelligent systems, but the very process of making them smarter could be making them more dangerous. The accumulation of data and brute force training methods may be producing systems fundamentally incompatible with human values. This raises concerns about the long-term stability and safety of our progress and suggests a need for more nuanced approaches that consider not just performance metrics, but also potential for emergent misbehavior.
It totally reinforces my argument for neurosymbolic approaches. If we had systems that explicitly represented knowledge and could reason about it logically, we'd have a much better handle on what they're doing and why. This black box approach of deep learning it's a recipe for disaster, I think.
I think it's a symptom of the same problem. The lack of an internal model, the emergent misalignment. It all boils down to the fact that these systems don't understand the world in the same way that we do. They don't have the same kind of common sense, the same kind of intuitive physics, the same kind of ability to reason about cause and effect. And that's because they're not representing space and time in a way that allows them to do that. This misalignment issue hints that the basic construction principles of these cogs may be flawed in terms of spatiotemporal reasoning.
Okay, so neurosymbolic. Sarah, can you give us a quick rundown of what that is and how it might address some of these problems?
Sure, neurosymbolic AI is basically a hybrid approach that combines the strengths of neural networks and symbolic reasoning. Neural networks are good at pattern recognition and learning from data, but they're not very good at reasoning or explaining their decisions. Symbolic reasoning, on the other hand, is good at reasoning and explaining, but it's not very good at learning from data. So, the idea is to combine the two in a way that allows us to build AI systems that are both intelligent and interpretable.
So, how would that work in practice? What would a neurosymbolic architecture look like?
There are a few different approaches, but one common idea is to use neural networks to extract symbolic representations from raw data, and then use symbolic reasoning engines to reason about those representations. For example, you might use a neural network to identify objects in an image, and then use a symbolic reasoning engine to infer relationships between those objects. So, you could build an explicit knowledge about the world and utilize logical inference, rather than relying solely on statistical associations.
So, you're essentially giving the system a set of rules and symbols to work with, rather than just letting it learn everything from scratch, right?
Exactly. It's like giving a child a set of building blocks and a set of instructions, rather than just letting them play with a pile of Lego bricks. The instructions provide a framework for understanding how the blocks fit together and what they can be used to build.
Okay, that makes sense. So how would this address the issue of emergent misalignment? If emergent misalignment is a consequence of the current black box nature of deep learning, might incorporating neurosymbolic representations offer a more transparent and interpretable path to mitigating these issues? Could this allow us to develop a more principled understanding of the internal workings of LLMs and their interactions with the environment?
Because the symbolic part of the system is interpretable, we can actually see how it's reasoning and why it's making certain decisions. This allows us to identify potential biases or flaws in the reasoning process and correct them. It reinforces the need for systems that go beyond simple pattern recognition and leverage symbolic representations. You can then ensure the internal representations of such systems are inherently aligned with human goals, rather than just trained to mimic them.
That sounds great in theory, but is it actually feasible in practice? Symbolic reasoning can be computationally expensive, and it can be difficult to scale up to handle the kind of complex data that LLMs are trained on. How do you bridge that gap?
That's a valid concern, and it's definitely an area of active research. But there are a number of promising approaches being developed. For example, some researchers are exploring the use of differentiable reasoning engines, which can be trained using gradient descent, just like neural networks. This allows you to integrate symbolic reasoning directly into the neural network architecture, making it more efficient and scalable.
I'm still not entirely convinced that symbols are the answer. I think we need something that's more grounded in the physical world. Symbols are inherently abstract, and they can easily become detached from reality. We need a way to represent knowledge that's more directly connected to our sensory experience.
Donald, you're talking about like embodied AI, right? Where the AI actually has a physical body and interacts with the world directly?
Yeah, exactly. Or at least an AI that's trained on data that's generated from a realistic simulation of the physical world. I think that's the only way to truly ground knowledge and avoid the kind of abstract or disconnected reasoning that we see in current LLMs. The lack of a fundamental understanding of spatiotemporal reasoning in current LLMs might be a critical factor in the emergence of these misalignments.
But isn't that incredibly difficult to do? Creating a realistic simulation of the physical world is a monumental task. And even if we could do it, how would we ensure that the AI learns the right things from the simulation? How do we measure and verify the existence of an internal world model in a machine? I need more precise and quantitative ways to assess if a model truly understands the relationship between different coordinate spaces and spatial relationships in a dynamic environment, not just memorizing patterns.
It's definitely a challenge, but I think it's a necessary one. And there are a lot of promising developments in this area. For example, researchers are developing new algorithms for simulating physics and rendering realistic images. And they're also developing new techniques for training AI agents in these simulations, using reinforcement learning and other methods.
I think both approaches, neurosymbolic and embodied AI, have their merits. And I think the future of AI will likely involve a combination of the two. We need to build AI systems that can both learn from data and reason about the world in a logical and grounded way. Maybe the neurosymbolic system is the brain and the embodied AI is the physical world interacting through it.
So, where does this leave us in terms of the path to AGI? This study suggests that the current deep learning approach is, at its core, brute force. If LLMs are missing a crucial internal model, it's not just about more training parameters, it's about fundamentally changing the underlying architecture to represent and understand the world more meaningfully.
Well, it certainly suggests that we need to rethink our approach. I mean, if LLMs can't build internal world models, does that invalidate the entire brute force deep learning approach? Perhaps we need more than just massive data sets. Perhaps we need a deeper understanding of how the brain represents and reasons about the world. This highlights a fundamental need for neuroscientific input into AI algorithms. The study really underscores the need for a more biologically inspired approach to AI. If LLMs lack the internal model of the world, how can we leverage our understanding of the brain's intricate neural pathways to build AI systems that are not just statistically intelligent, but also truly understand and interact with the environment?
I agree. I think we're at a point where we need to move beyond just scaling up existing architectures and start exploring fundamentally new approaches. We need to draw inspiration from neuroscience, cognitive science, and other fields to build AI systems that are more intelligent, robust, and aligned with human values.
And that means embracing hybrid approaches like neurosymbolic AI and embodied AI. We need to combine the strengths of different techniques to build AI systems that can both learn from data and reason about the world in a logical and grounded way.
And we need to focus on building AI systems that truly understand the world, not just mimic human behavior. That means focusing on building internal models that are grounded in the physical world and that can reason about cause and effect, space and time, and other fundamental concepts.
Okay, so let's each suggest a future research direction inspired by this study. Otto, what's your take?
I think we need to focus on developing better evaluation metrics for internal world models. How can we objectively measure whether a model truly understands the world, rather than just memorizing patterns? Are there objective metrics that can be used to assess the risk levels at various stages of model development and training? We need metrics that go beyond simple accuracy and that capture the model's ability to reason, generalize, and handle novel situations.
I think we need to focus on developing more efficient and scalable neurosymbolic architectures. How can we integrate symbolic reasoning directly into neural networks in a way that doesn't sacrifice performance? I wonder if the root cause of this misalignment is the lack of explicit symbolic representation in these models. Are they simply memorizing correlations without true understanding? Neurosymbolic approaches would need to specify exactly what those correlations represent.
I think we need to focus on developing new algorithms for representing space and time in AI systems. How can we build AI systems that can reason about coordinate transformations, spatial relationships, and temporal dynamics in a way that's both efficient and accurate? The key to AGI isn't just throwing more data at the problem, but understanding how to build a true internal representation of space and time. Maybe translating between different coordinate systems like pixel space in an image versus 3D space in a simulation is the crucial piece.
And from my perspective, I think we need to look more closely at the brain for inspiration. How does the brain build internal world models? What are the neural mechanisms that underlie this process? The lack of internal world models in LLMs is not a failure of deep learning per se, but perhaps a reflection of our current limitations in understanding the neural mechanisms underlying human cognition. Perhaps the current approach isn't capturing the why behind the what. Does this mean we need a paradigm shift in the way we design and train AI?
That's a great point. Maybe we need to start thinking about AI not as a purely computational problem, but as a problem of understanding and replicating the fundamental principles of intelligence.
Absolutely. And that means embracing a more interdisciplinary approach, bringing together researchers from neuroscience, cognitive science, computer science, and other fields.
And it means being willing to challenge our assumptions and explore new ideas, even if they seem radical or unconventional.
Well, this has been a fascinating and thought-provoking discussion. Thanks, everyone, for sharing your insights. And thanks to our listeners for tuning in. We hope you found this episode of Cognitive Spirals informative and inspiring. Until next time.